Hi all, welcome to all. Today the another session, the session 2. Here today the topic is dynamic analysis for DAF calculation. So why we need to do the dynamic analysis for DAF calculation? We know that for other department like structural, for piping, mechanical, we have the contingency factor on it. But when the structure is in motion, we have to capture the inertia force. For that we need to give the as a contingency to the wave. Actually, for that reason we have to come up with the DAF calculation. That is the main aim of the calculation. What we have to do is we have to find out the factor, and we have to factor we have to means whatever we find out that factor, that factor we have to multiply to the wave load. For that is the reason we have to find out the DAF calculation. This we have to find out through the dynamic analysis, because we need to generate the inertial forces. So the principle, the basically the dynamic analysis is carried out to determine the natural period mode shape. Yes, we know that. Why we need to do the dynamic analysis? To know the natural period of the structure and mode shape, how it is behaving, whether it is behaving in x direction, y direction, sway mode, or it is torsion, something like that. We have to find the from the dynamic analysis for further use in this seismic analysis and spectral analysis. This will be extensively used in seismic analysis and spectral fatigue analysis. Further, the natural period will be used for the calculation of dynamic amplification factor for InPlace. As I told in the beginning of this presentation, apart from this, we have to calculate the DAF and apply the factor to the InPlace analysis in the wave load combinations. How to do that one? From the InPlace model, we have to take the SAX input file as well as the PSI input file. Then we have to do a slight modification on the PSI file in order to linearize the foundation, and then in the same InPlace SAX InPlace file we have to create the mass load case. We have to generate the mass load case, as well as uh, we have to create the dynamic input file to create the mass, and then we have to specify the mass joint. Basically the mass joint is the main joint of the brace and jacket leg, wherever it is connecting the primary joints. Basically we need to select as the mass joint. Why? We have to lump the masses on those joint. There is a certain command is there in that program. I will tell you in the next slides how to give, what is the constraint we have to give for this mass joint. After this one we have to take the run in the dynamic run. Once the program is run, we can find out the natural time period from the dyne output, dyne list file. Basically time period, and then mode shape, and then mass participation, everything will be load sum, everything can be read in the dyne list file. Once if you know the time period, we can calculate the DAF by using the DAF formula. Okay, so this is the dynamic analysis flow chart. We will let me explain step by step procedure to calculate the DAF. So for this presentation I have considered a four-legged jacket. For this four-legged jacket I am going to calculate the DAF. So first of any of your analysis, first you have to create the separate folder. This will provide you to file handling will be easy and avoid the confusion to which file you have to modify what things. Actually, if you see the fatigue analysis, you might be having many, some 4 to 5 folders. So each and every folder you have to create separately, and you have to store the file by naming clearly what analysis or what module you are using. With that the file name, like that you have the folder name, you have to create very clearly. See here, it is first is InPlace. Here the main InPlace file will be there. Second is file super element file. In that folder I'm going to copy the SAX InPlace file, as well as the PSI in place PSI file into the pile super element. Once the pile super element is done, again what I'm going to do, I'm going to copy the dynamic input file over here. So the results, the output will be stored in separate file. If you are not having this folder, separate folder, all the outputs will be in the same page. You have to be, you have to search in it. To avoid that confusion, you have to be create separate folder. That will be the very good for the file handling system. Then first is super element creation. So what we need to, the first step after copying the sax file and psl file to the pile super element, we have to uh, take the file psi file input file here, and then what we have, you have to just in that psi opt file just give one enter and then insert the line file soup. This is the insert line you have to insert. After that you have to mention the load case here. So these load cases are the load case which we are having the storm load case, which we are having the x and y and x and y direction waves here. Here there will be a first pair of load, second pair of load, third pair of load, fourth pair of load. These load cases we have to give here. I will explain what is the load pair actually in the next slide. See, this is one platform here. This is the wave 0 degree, 90 degree, 180 degree, 270 degree, and there will be a 45 degree, like that. There will be orthogonal degree also here. It is there. So, suppose this is the 101 load case, 102, 103, 4, 5, 6, 7, 8. There will be 8 load case will be there. Each and all platform minimum 8 load case will be there for rectangle platform as per API. Here also there is the load case is there, 8 load case. If you see here, here there is a first pair is x 101 and y direction, so 103 here it is there. And if you take the second one 103, 10 x is 105 and y is 103. This is the second load case here. And third is x is 105 and fourth is 107. This is the third load case here. And fourth load case, x is 101 and y is 107. So this is the first pair, second pair, third pair, fourth pair. So like that we have to. So anyway, orthogonal direction we will not consider because this will not govern. So we have to linearize file with these load cases. That's why in that second opt file we have to give enter and then we have to specify these load cases. And then what we have to do now, we have to take a run so that the pile super element will be created. Means that the pile linearization will be done. After that the same open the sax file and then modify the joint. See wherever the joint is coming, so you can see there is a one triangular shape, the joint here. So click that joint and you just enter the fixed D as 222000, which is represent the mass joint. Automatically the sax will identify those joint and apply the inertia load here. Actually the mass will be lumped here, those joint, that is 222000. This is the fixed D. This way you have to select all the jacket main joints over here. You no need to select this joint at all. Even though this is joint, this is not connecting any brace or any secondary members over here or primary members. So only focus on the primary joints. Then mask case. So you just open the sax input file here. Now you have to bring all your load case, operating load case in one load under maybe 1000 or whatever the name, just you give it. So you create one load combination having all the load case by having by reducing the live load of 75% over here. So you bring all the load case here into one load case, that operating load case. That load case you define in the first point, dy in the sense just for dynamic 1000 is the load case which is having the all load case. I want to convert those load case into mass. Now this is the Dynapack input file where I have to mention if it is which direction x, y, z 111, and this is the 50 is the number of modes that I want to request for the program, and this is 1.2. 1.2 is the any structural any contingency or anything is there, you have to put a 1.2 or 1.1 10% or whatever maybe, or if you don't want any contingency just put 1.0. This is the dynamic input file, that's all. This is only will contain only 3 lines, that's all, nothing to do. The once the moment if you are creating, this will be all will be automatically created. One thing you have to give only the factor, any factor is there or not, you have to give for the weight contingency, that's all. Once created this dynamic input file, you have to create the, you have to go to the sax, and then you have to pick the dynamic analysis type dynamic and subtitle extract mode shape. From there you have to give the this sax model input file. This input file, which one is, it's not from the input file which we copy and pasted in the super element file which is having the mass joint. This is the file here, mass joint file. That thing you have to give it here, this one sax model file. Then this is super element. Now the here the second one you have to give dyne acf, means that dyne super element file here. Once if you are running the program, that this second one you might have created the file super element over here by modifying this load cases with the sax input file. From there output of super element file you have to give it here, dyne acf super element file you have to give here. Then dynamic input file, the dynamic input file what I have told now, that input file you have to give here. Now you take a run. Now after taking the run everything is finished. Now your time period, mode shape and mass participation factor, load sum, everything will be ready to calculate the DAF. Now if you see here the output file, there will be a dyne list, dynlist list file will be there. Once if you finish the run of the dynamic module, from there you can find the all load sum over here. If you see here there is a plate element, so whatever your model in the plate, there is a, if any added mass in that, this is a member element, member added mass, member element axial added mass, and there will be a flooded member element entrapped fluid. If any jacket leg will is there flooded member, there will be entrapped water will be there inside that. For that also the program will create the mass generation. For that it will consider the load, so that load, then load case converted to weights, this the ngda load, whatever the load you have applied, the for that load it is created as a mass. So you have to check all your this masses, this weights, whatever you are created which is equal to your 1000 load case, which is beginningly you have used dy 1000. So whatever the loads you have bought under that, that one you have to just ensure that all the loads is you have converted into mass. So this is the load sum. From here you can clearly validate. Then mass participation, so the whatever the joints you are given, that the mass joint, so that joint mass will be lumped over there. When it's requested from 1 to 50 mode here, you have to capture all the masses there. In order to ensure that one, if you see here in the x and y z direction, there is a 99% of mass participation in x direction, and y direction 99% of mass participation, and z direction is 0.96% of mass participation. So basically at least the mass participation should be 90% from your analysis. If you are not achieving this one, what we have to do now, you have to create the more joint. If you are creating the more joint, then the mass participation factor will increase that. What you want to understand from this point of view, yes, I have considered all the masses, all the inertial forces in the dynamic analysis. Now my time period is correct, something like that. You have to confirm from here mass participation factor. Okay. Then period of the structure, the same input file, if you go there, you can find the period. You see 2.3. So this is the my period of the structure 2.308, and second period is 2.05. This is the very important thing to find out the DAF. Okay, so there will be for each and every mode there will be a separate period will be there. First we have to interested only the first mode, which will having the means a higher period. This for these two values will be we are interested. Then this is the mode shape one. If you click that, there is a PSTV file. If you go there and click, you can find out the mode shape. This is the first mode, which same period 32.308, which is here. Say will be reflecting here. Okay, and if you see that this is second mode and this is third mode. This is the mode shapes seeing by graphically. From here you can know how the platform is deflecting from which side, whether it is X or Y, everything we can see it over here. Next is DAF formula. This is a DAF formula, Dynamic Amplification Factor. Here DAF equal to 1 by root of 1 minus T n square divided by T square. Here and is the eta. Here is the three unknown, T n square, T, and this is eta. Eta is nothing but the damping factor of 5%. For steel structure you have to take 5% here, and there is a T square. This T square n capital T base of n square is the natural period of the structure. First mode, what is our first mode natural frequency? This is the mode 1, first mode. It is 2.308. This is the time period. So that is the thing we have to substitute over here. And T square is nothing but the wave period. Actually this wave period actually for the wave, whatever we are having, the 0 degree or 45 degree, that period we have to take over here. Okay, this is the formula. And this is the DAF calculation here. Here there is a two DAF is calculated, DAF X and DAF Y. So whatever the maximum one we have to take for the for our analysis. Okay, and there is the theta also, it is calculated. This is calculated for the means diagonal direction, but however for for conservative we are doing only the in first mode in the X direction or Y direction, whatever it comes actually. So we no need to do X, Y, Z and theta. One DAF, only simple DAF is enough actually. By substituting the first, actually here I find out 2.3 for the Y for first mode and second mode of X. I'm substituting this 2.06 here, 2.06 for one set of equation for X and 2.06 for other set of equation for Y. For that I have calculated and then find out the DAF. And there is a theta for the theta also, the angle of incident of the wave. For that particular direction I resolved this one and then I have calculated the DAF here. So for each and every direction, so for suppose if I am applying 0 direction, 0 is my X direction, so I will take 1.108, that is the DAF. And for 30 degrees, so 30 degrees is the combination of X and Y, so I will take 1.168. This is for DAF for 30 degree. And 60 degree and 90 degree it comes to Y, so I will take 1.186. So this way we have to apply these factors into the wave load. So go to the first folder of the InPlace file, and then if you see here there is a 1.063 and 1.086 and 1.125, 1.084, 1.046, so on. So the DAF will be entered here, so that now our wave got amplified over here, and then we have to take the run. So that we have what we are doing is we are the inertial force we have captured here, and then the lateral load we are amplifying that factor with that lateral load, with the wave load over here, and then we are finding, because we don't know how much the contingency for the wave load we have to give, but there will be a dynamic effect due to the wave, that inertial force we are capturing in terms of here factoring the wave over here. So after this updating these values, we have to take final InPlace run. So this completes the DAF calculations over here. Okay, if you have any general discussion or question and answer, please comment in the section. I will give reply, or else please message me in the LinkedIn or to my mail ID. I'll be answering your questions. Thank you. Please kindly share this one to your friends and beginners so that they will get benefited. Thank you very much.